Okay, welcome to the next lecture, 16th lecture. We're now changing a little bit topic. So let me just recap quickly where we are. So I've done this a few times before, but just to make sure we're all still following. So we have in chapter 1, I have described to you differential equations, particular initial value problems, how we can write every initial value problem into a first order system of ODEs with initial conditions. Studied their properties, in particular existence, uniqueness, and stability. And then in chapter 2 started designing numerical methods for it. First of all, explicit one-step methods, which are simply advancing the solution forward in time from the initial condition. Improved conversions, and in what sense we have convergence. But we saw immediately that in these convergence results we had a very strong exponential dependence on the end time. So if we wanted to study very long time intervals, this analysis here was not gonna be sufficient. Was not going to be sufficient. And so in chapter 3 we've now at length studied long-term stability. This brought us to into the context of implicit one-step methods. Okay, so first of all, we need to look at particular ODEs in order to study long-term behavior, because if we have an ODE that does not, in some sense, decay over time, then we cannot expect to be able to get stability over a long time. But for monotonic initial value problems where the solution essentially decreases to zero, or the major parts, we do get stability, and we've introduced the terms A, B, and L stability. The way to solve those things is not via explicit methods, but via implicit methods. Now, the important difference between explicit and implicit methods, and that's why I'm bringing this up now, is that in an implicit method, I'm not going to write the formula down again, but the value yn plus 1 that we want to compute depends on the right hand side not only on yn, but also on yn plus 1. Or in more general settings, for when there's more stages, the stages in the calculation of yn plus 1 depend on each other, and therefore we need to solve nonlinear problems. So the important message to take away from here is that these systems lead to nonlinear equations in each time step. The last two lectures we have now gone a little different direction and studied not the long-term stability in the sense of solutions that decrease to zero, but Hamiltonian systems where certain integrals, where certain quantities are conserved. And in particular, the energy is conserved in Hamiltonian systems typically, and the area, and this is called symplecticity of the flow, that area of certain areas in the initial condition domain are preserved as they're propagated through the differential equation. And in order to integrate those numerically, we need numerical methods with certain properties, so-called symplectic integrators, and we've studied some of them. In particular, the one-stage Gauss collocation method, which is the implicit midpoint rule. Okay, but as I said, crucially in all those methods and in these symplectic integrators in general are also implicit. In all these implicit integrators, we need to solve nonlinear equations to calculate the stage values. And so in order to solve those nonlinear equations, we need a little chapter which will only take us a lecture or two to discuss how to do this. And we've already seen in the numeric zero the Newton's method, and so I will just recall a bit on that and add a globalization strategy to them. Okay, so let me start in section 1 with some basics of nonlinear iterative methods, nonlinear iterations. So the efficient solution of nonlinear problems is an important ingredient of implicit time-stepping schemes. So I'm just going to paraphrase this. Efficient solution of nonlinear equations is important ingredient in implicit time-stepping schemes. Without trying to be complete, I will now present some important facts on nonlinear iterations. So we've already said in numeric 0 that nonlinear systems, different to linear systems where we can factorize the matrix and solve the problem explicitly, nonlinear problems can typically only be solved iteratively. And we've seen the fixed point iteration, and we've seen the Newton method in numeric 0. So in this coming section, we will now introduce two generic schemes for nonlinear problems: the Newton's method and variants of it, and gradient methods. And if time permits, probably I will actually come back more detailed to gradient methods in chapter 6 as well. So we'll discuss their respective pros and cons and combine their features for even better methods. Okay, so what are we solving? We are considering now the problem of, so I'm not going to phrase it in the context of the implicit integrators and stage values. I'm just going to pose it as a standalone mathematical problem, and you just have to put the correct variables and the correct functions in for the stage values in order to apply it to implicit integrators. So we consider the problem of finding an x in Rd, so a d-dimensional vector, such that again a d-dimensional function fx is 0. So f being a function from Rd to Rd. So a square nonlinear system, same amount of equations, nonlinear equations as unknowns. Again, a recap from numeric 0. An iteration xk plus 1 equals g of xk. To find the fixed point x star equals g of x star is said to be convergent of order p greater or equal to 1 if, and this is important here, so there is a p up here. So if the norm, whatever norm you want to measure the vector in, for example Euclidean norm of xk plus 1 minus x star is less than or equal to q times xk minus x star to the p. So typically, so not typically, but p has to be less than greater than or equal to 1. And then if p is strictly bigger than 1, this automatically means that provided xk minus x star is less than 1, this will decrease to 0, but this will be decreasing. If p is equal to 1, which is the linear convergence case, so for the case of linear convergence, then it doesn't suffice that we have just any old q here. We need to have the q less than 1. Otherwise, this will not decrease. Because if this is 1, then this does not decrease, this second term here. And in order for the left-hand side to decrease, we need q to be less than 1. And in that case, q is called the convergence rate. So if we have a linear convergence, then we talk about the convergence rate q. If we have higher order convergence, we talk about the convergence order of a method. And then the constant is still important, but it's not as critical for higher order convergence. So we have already seen, so in lemma 3.3.9 that the fixed point iteration e.g. for the implicit Euler method so that we compute y mth iterate, so this is not the mth value. Maybe let's call it so ym equals psi of ym minus 1, where psi is defined as, well, actually I should call this g because we call it g up there. So the iteration ym equals g of ym minus 1, where we define g as being y naught plus h times f of t1 ym minus 1. So you can think of this as being approximations of y1 with the initial starting approximation being y naught converges, just fix that here, g1 1 1 1 converges to y1 provided the step size is sufficiently small, namely HL is less than 1, where L is the Lipschitz constant for F. Let's write it in blue. But the convergence is only of order 1. Is only linear. And the convergence rate remember, for p equals 1, we need a rate, is less than or equal to LH. So if we know nothing better, this may be close to 1 when the step size is large, or when the Lipschitz constant is large in particular. Moreover, if we don't get the step size right, like we know, we've already said this in the discussion of solvability of these equations, it may actually fail if HL is in fact bigger than or equal to 1. So if you pick too long a step size, you might actually end up not being able to solve this nonlinear system. So in numeric 0, and so I'm repeating myself for the third time, we've seen already a faster converging algorithm, namely the Newton's method, and proved that it converges with order p equals 2 for sufficiently good starting guesses. So, and this is in fact one of the main issues we will try to address today, or in the two videos I'm doing on Newton's method. So we will first of all recall that it's quadratically converging Newton's method when it's close enough to the solution, but we will also address the problem that for this convergence theorem that we have from numeric 0, we need sufficiently good starting guesses, and for that purpose we will globalize or make a globally converging Newton's method. Okay, so first of all, let's recall what the Newton's method actually is in definition 4.1.3. So the Newton's method for finding the root of the nonlinear equation fx equals 0 with f from Rd to Rd, so our equation, did this have a number? Yeah, 4.1. Reads, given an initial value x naught in Rd, and I'm using superscripts here so to distinguish it from the time steps. So x superscript naught in Rd computes iterates xk in Rd, k equals 1, 2, 3, etc. as follows. First of all, we define or we compute the Jacobian. So this is a matrix. This is a matrix because we have a vector valued function f, and so the gradient of f, remember, is the transpose of the partial derivatives df. So this is df of xk transpose, and then it computes dk, the step, the Newton step, by solving a linear system with this matrix G of xk, with this Jacobian matrix. So it basically, so typically this is not done by inversion. Typically this is solved as a system. So G of xk times dk is equal to minus f of xk. So we're solving this linear system in each Newton step. And then the old iterate xk is updated by adding this Newton direction dk to it that I've just computed. We also define the term quasi-Newton method, and we define this as any modification of this scheme which employs an approximation gk tilde of the Jacobian of g of xk. So this is obviously a costly part of this iteration, and often not even available, because you need to actually have derivatives of the function we want to solve, and so often we have to approximate this. This is called a quasi-Newton method. Now I'm recalling the theorem from numeric 0 that we proved there. Let U be some subset of Rd, and let f be continuously differentiable on this set U. So f is a continuously differentiable function with, moreover, so it's not just continuously differentiable, it's actually also its derivative, or its Jacobian, is also Lipschitz. So now this is a matrix norm here, and this is a vector norm. So the matrix norm of Jacobian of f minus Jacobian of f at x minus Jacobian of f at y is actually bounded above by the distance of x and y times the Lipschitz constant L for any x and y in the same set or in a smaller set, but we choose u to be such that both those conditions hold. And this L is some arbitrary constant greater than 0. Now, Newton's method does not prove existence of a solution. It just says if there is a solution, it converges to it. So if there exists an x star in this set U, where f of x star is 0, and if the I should give this a number. So this is 4.3 and this is 4.4, and the inverse of the Jacobian at the root is exists, so it's non-singular, and it is bounded by some constant m. So this can be relaxed, but for simplicity in this simpler proof in numeric 0, we assumed this condition, and in fact it is critical. It is critical to get order 2. So under these two conditions on the Jacobian, there exists a radius r that's strictly bigger than 0 and less than 1 over 2 lm, such that for all initial starting guesses x naught that are in U and not further away from x star than r, we have convergence to the root with order p equals 2. So we have quadratic convergence of the Newton's method to the root with order in the ball of radius r. Okay, so I'm not proving this. If you haven't, if you can't recall it, then please look back at your numeric 0 notes. And for those that have not done numeric 0 with me, please have a look at some other textbook if you want to know the proof of this. In fact, the notes for numeric 0 can be found on my webpage as well, if you want to read it up there. There are also versions, so we're assuming the existence of the root in this version. So there are also versions that do not require the existence of the root a priori. Beforehand, and this is, for example, the famous Newton-Kantorowicz theorem. You can find a statement and a proof of that in Ranacher's lecture notes for numeric 1 for this course. It's theorem 5.5. That book is in German, but the math should be clear. But we will only discuss some of the main assumptions and features of that theorem. So let's just, oh, there's no space here. Didn't leave enough space here. Let's put another page. So the Lipschitz condition on the Jacobian is essentially nothing else than so if the function f was actually linear, then grad f would be the identity, and so you essentially would have Lipschitz condition with L equals 1. So the Lipschitz condition can be seen as a level of deviation of f from being linear. And as I just said, indeed, if oh, sorry, it's not 1. The grad f, if it's linear, would actually be 0. If f were linear, then L is in fact 0, and provided M is non-zero, the method converges in one step. So if we are linear, then this result actually shows us that we have convergence in one step with the Newton's method. If we have a very small Lipschitz constant, then we will get very, very fast convergence, and we might be able to also get a very close to exact solution in one step, which would mean that, so if we have a nearly linear function in our initial value problem over a time step, we might get away with just evaluating one linear system, and so the implicit method would behave like an implicit method for a linear problem where we have to solve one linear equation in each time step. But the larger the constant m, so the more grad f, the Jacobian is not invertible, the smaller one of the eigenvalues of the Jacobian g equals grad f is. And then in that case, so if if f in some area has nearly constant gradient in one direction, so I'm trying to draw this in 2D in some sense. So if you have, for example, a situation where the f is some sort of bowl, and along this direction the minimum is somewhere here, but along this direction the function is almost flat, then it gets very difficult to pin down the solution at. So I'm drawing the isolines. Maybe let me draw the isolines of this function. So I'm trying to draw some sort of function that decreases in a bowl towards this bottom, and if the in one direction the eigenvalue, if the function is almost flat in one direction, that would create a nearly singular Jacobian with one eigenvalue in that direction being nearly 0. Therefore the function f becomes flat in that direction, in the direction of the eigenvector. And the root finding problem becomes unstable. But as I said already when I stated the proof, the Newton's method still converges even when m goes to infinity. But only linearly. So with p equals 1. So the special, or the situation where the second assumption in our theorem is not satisfied, as I said, it can be relaxed. The Newton's method can still converge, but it will only converge linearly in that case. And then the most important statement, and that's the one I've already highlighted that I want to address in this whole chapter. So Newton sounds like the perfect method to solve this problem, were it not for the problem that for an arbitrary initial guess that's not close to the solution, the method may fail completely. Or compute or converge to a different solution, to a different solution of the nonlinear equation. However, close to the solution, the convergence is very fast. In numeric 0, I demonstrated what quadratic convergence really means. It means that typically you only need a handful, 2, 3, 4 iterations to get a sufficiently small error. While linear convergence, it suggests linear and quadratic doesn't sound very different, but quadratic convergence, we're talking about a small number, 2, 3, 4, 5 single-digit iterations, while linear iterations typically need hundreds of iterations. So we're really talking about a lot less work, much faster than the fixed point iteration. So while the fixed point iteration might be very easy and simple to implement, it can be very, very slow. Okay, so we need to somehow console this problem, namely that if we don't have a good initial guess for our iteration, we may fail to converge. But we would like to keep the really fast convergence of the Newton's method. So in order to do this, I will introduce a second type of method, namely so-called descent methods. So nonlinear root finding of a vector valued function f is closely related to as, for example, required. I'm not going to say that again. As, for example, required in implicit time-stepping schemes is closely related to optimization of scalar functions f also from Rd, but now to R. And the following problem is equivalent to our nonlinear equation 4.1 whenever the little f is in fact the gradient of capital F. So I'll link those two in a minute. Okay, so if I want to find the zero of a vector valued function little f, that is the gradient of a capital F scalar valued function, then I can also minimize the scalar function over all y in Rd. We can minimize f of y. I'm just specifying again what capital F is here for this equation so that we can quote it when referring to 4.5. So here in the following we assume that we actually know this integral of little f. I will show at the end that it is actually not required, that the final method that we're going to come up with, the Newton method with line search, does not actually require it explicitly. So we just have to know that there exists a capital F such that little f can be written as the gradient of capital F. And this is very easily justifiable in applications. I'll give an example how to build one later. So obviously by choosing f to be grad capital F, we could, of course, apply Newton's method to solve this optimization problem. And this is, in fact, one of the workhorses of optimization as well. So when you're close enough with your minimum, with your solution to the argument of this capital F, then again, Newton's method is your method of choice. But in order to make Newton's method more stable or more robust to choosing arbitrary starting values, I now introduce an alternative family of methods. And these are the so-called descent methods. A descent method is an iterative method for finding minimizers of the functional capital F, scalar valued capital F as a function of Rd. That starts again from an initial guess x naught in Rd to compute iterates xk in doing the following steps. If, so careful, this is not the Jacobian of little f that we had before. Here we have the gradient of a scalar valued function. So this is a vector. So if the gradient of capital F at the iterate is non-zero, if once the gradient of f is 0, we have found a stationary point, and if the curvature is negative there, then we have found a minimum. So while this gradient of f is non-zero, we want to go down. So we know that the gradient of f is non-zero, so in some direction the function can be reduced. Okay, if you have a smooth enough function capital F, and you know that its gradient is not flat, then you know that you can decrease the function in one direction, and so you pick one such direction. So this is not a unique choice, but we basically pick we choose a direction S in Rd such that the inner product, so this should be actually, I'm using these brackets normally, I need to write this here, is less than 0. And then you pick a positive parameter, alpha k, because in this direction the function is decreased in the direction sk. So if we pick a positive alpha k, then the previous iterate xk plus alpha k times sk gives us a smaller value. So this clearly decreases the value of capital F. And remember, that's the whole point. We want to solve the minimization problem. Where's our minimization problem? Here. We want to solve the minimization problem given here. So we want to find the x that minimizes capital F over all y in Rd. And so if we have a certain xk and we go in a direction where where the gradient of f is negative, then or the direction of the derivative is negative, then we will get a lower value of f. And so by following this procedure, we hope to find the minimum. Okay? And in fact, we can immediately state the following lemma, which I'm not going to prove, but which is a classical result about minimization in optimization. So if you've been to an optimization course, you have definitely done this. If f is continuously differentiable, for a given point x, we assume that the gradient of f is non-zero. Then there exists a constant theta greater than 0, such that for any descent direction d satisfying 4.6, so I need to give this a number, and for any step size alpha between 0 and theta. So we can't take arbitrarily large steps, but we can take sufficiently large steps. So here we have a theta greater than 0, so we can pick alpha at least of size theta, which is bigger than 0, and therefore we know that because this is positive here, all of these numbers are positive here. So here everything's positive, strictly positive. So this whole thing is strictly positive. And so we get guaranteed decrease. In particular, a positive scaling factor alpha for the descent method, and thus a strict decrease in the function value can always be found. So unless we are at the solution, at the minimum, or at some stationary point, we will always find a descent direction. Okay. So as I said, I'm gonna skip this proof and refer to the literature. Nogedal and Wright is the book I'm gonna refer to mostly in this section. So I'll write it out once. I'm just gonna quickly check what it's called. So it's called numerical optimization. And it's from Springer, and the second edition is from 2006. Okay. So the most prominent member, oops, of this family of methods is the so-called gradient method, or steepest descent method. The gradient or steepest descent method. So the steepest descent method is slightly is one version of descent methods where we pick a very specific direction. So remember, in the descent methods, we've just chosen any old sk that has the property that grad f with sk in a product is less than 0. But in fact, if we pick this direction to be minus gradient of f, so if sk is minus gradient of f, then then we minimize the steepest possible decrease locally is achieved. And if we pick the alpha k also not, so we have a specific choice of dk now and a specific choice of alpha k, and then we get I'm gonna change the letters in the script to dk also in the top, because I think it's a bit confusing that we're using d and s's. So the descent direction is chosen to be minus gradient of f of xk, and the step size alpha k is chosen such that along the one-dimensional line we're minimizing. Okay, so again, this requires a little bit of a drawing. I'm just gonna try to do that. So again, we need a 2D system, otherwise you can't really see anything. So if this is my function, and here are the isolines, somehow oh, this is gonna get a bit confusing here. Okay, let's assume this is our function. Then at a particular point, wherever we are, we pick the direction of steepest descent, which is basically in this case pointing downwards this direction. And then we minimize along this line the function. So we may end up getting somewhere here where we hit the bottom of that valley, and before it goes up again the function, and this would be our next iterate. And then we pick down there the next direction, and we start to iterate. So we're minimizing along a one-dimensional manifold, which is much simpler than solving the d-dimensional minimization problem. This can be explicitly solved often. And then we choose the next iterate xk plus 1 to be xk plus this step size alpha k in the direction of the negative gradient. Okay, it's also called method of steepest descent. I've already written that down. And the minimization process as used to compute alpha k is called line search. So we have got the method of steepest descent, and this search is called the line search. It's one-dimensional and therefore simple. And in the practical methods, we are not even gonna solve this explicitly. We're not gonna solve this problem here exact. We're gonna just approximate it. So we find an approximate minimum alpha tilde k. And that's basically gonna be the accumulation of our section here. That's what the method that we're gonna propose at the end will look like. So again, we have a theorem for this steepest descent method. So let f again be a continuously differentiable scalar function, and x naught an initial condition, an arbitrary initial guess, x naught. For the purposes of this proof here, let's assume that the set k, which contains all points that are less than or equal to f of x naught, is compact. So there could be multiple minima, and if you're not if you're in some bowl where the solution is so something like this. So if we want to find this minimum, so all our methods will only work for local minima. We won't have a method that finds the global minimum. It will just find a local minimum. So that's one other thing I forgot to say. The methods we're computing will only be able to compute local minima. If you start in this bowl, it will compute this minimum, okay? But in the setting of our initial value problem, that's fine, because what we want is roots of our equation f. Remember, capital F is chosen so that grad of capital F is little f, and so any solution where this is 0 is a solution of our nonlinear equation, and so any local minimum is fine. So what this k set is, it's saying that the set of values in Rd that are less than or equal to x naught is compact. So it's essentially this set. This example that I've just drawn here would not be satisfying this condition, because here we would have a non-compact. Sorry, this is compact. Sorry, this is not simply connected, but it's compact. Okay, but what we want to avoid is situations where the function essentially slopes away in one direction. So if you, for example, have the situation where this is the case, okay, and you start with this initial condition, then the set on which the function values are smaller is not compact. So this is a technical condition that is not a necessary condition, but it makes the proof simpler. Okay, so if k is chosen such that f of x is less than or equal to f of x naught, is compact, then each sequence defined by the gradient method has at least one accumulation point, and each accumulation point is a stationary point of f of x. Okay, so it's a point where the gradient of f is 0. It could also find a saddle point, but for the purposes of our initial value problem solution, that is not a problem. Let me give you a proof of this result. So first we observe that in any point xk with gradient f of xk non-zero, it follows from the lemma on descent methods (4.2.2) that there exists some gamma greater than 0 such that f of xk is strictly bigger than f of xk plus gamma dk. We've already said, I'll just scroll back to lemma 4.2.2. We said that provided we choose theta or alpha sufficiently small, then we can always find a direction in which there's decrease, or we can always decrease the value of the function by going alpha times s into that direction, into this descent direction. Clearly this is a descent direction because minus grad f in a product with grad f is definitely less than 0 for grad f non-zero. And so we have that there exists a gamma such that we can strictly decrease the function value in the direction of decay. So this implies for such an xk, the line search obtains a positive alpha k, so strictly positive alpha k. And thus the gradient iteration is monotonically so we know there exists a gamma that leads to a strict decrease, and the line search finds the smallest such gamma, and so it definitely leads to a positive alpha k, and therefore the gradient iteration is monotonically decreasing, and because k is compact, the set of all values where f of x is less than f of x naught is compact, it stays within the set k. Since k was assumed to be compact, so it stays in the set k because the value gets smaller. Sorry, it has nothing to do with compactness. So it stays in this set k because the value of f is strictly decreased, and because the set k was assumed to be compact, the sequence has the sequence xk has to have at least one accumulation point x star However, the preceding discussion implies that for that accumulation point, f of a gradient f of x star has to be 0. So it's a stationary point. Okay, so as long as grad f of xk is non-zero, this can be done, and so the accumulation point has to satisfy grad f of x star equals 0. And you see already immediately how you can extend this proof to non-compact sets, because if we assume that x naught is not on any of those cusps where the gradient of f of course is 0, then we can just restrict that the gradient, when the gradient iteration is monotonically decreasing, it has to stay within a subset of k which is compact. So if you're in this side of the bowl, it will stay in this side of the bowl. If you're in that side of the bowl, otherwise it has to go through some saddle point where gradient of f is non-zero. So there is some awkward sort of special cases you need to deal with that I wanted to avoid in this proof. But basically it shows that for any point x naught, we can basically find a local minimum or a local stationary point, more to the point, a point where grad f is 0. Now, this was a very specific descent method now. So the steepest descent method, which chooses essentially the descent direction to be the negative gradient of f. And if you think about this in the terms of geometry, we are minimizing in the Euclidean norm, because we're simply looking at the gradient in the direction, or Euclidean metric, and a very straightforward generalization is to change the metric. So remark 4.2.5. And I'm not going to discuss this in detail, but we can also choose dk to be minus any bk grad f of xk. In 4.8, did I give numbers? Let's have a look. I probably forgot to give numbers again. So where were we? We have 4.8 is this minimization problem here. 4.7 is this condition for the descent method, and 4.6 we've given a number. Just make sure I've put all the numbers. Which one's 4.5? 4.5 was the minimization problem, 4.6, 4.7. 4.8 is the steepest descent method, and I didn't give this one a number. Okay, however, we can also choose the steepest, the descent direction to be minus gradient multiplied by some matrix bk, where bk has to be positive definite for any positive definite matrix bk leading to the so-called generalized steepest descent methods. That minimize the descent direction in a different norm. In 4.6, in the weighted norm induced by the weighted inner product x, y, b. Maybe I'll stick with my Langle and angular brackets here. Okay. X transpose pk y. Instead of the Euclidean. Inner product. X transpose y. And this is important because if you look carefully, you will see that in particular for functions that are convex or locally convex, so if the Hessian, which is the second derivative of f, actually I'm going to use the notation I used in the previous chapter, if the Hessian of capital F, same notation as we used for the Hessian of the Hamiltonian, if the Hessian of capital F at xk is positive definite, which means that the function capital F is convex, so this kind of bowls that I've drawn before, so this would be, for example, a convex, this thing here would be a convex capital F, where the Hessian, the Hessian of F is positive definite. We can choose bk to be actually the Hessian of capital F of xk, and we can choose alpha k to be equals to 1, which reduces to Newton's method. If you look back here, remember, I'll just write it down again, our little f was assumed to be grad f, and our Hessian is therefore simply the Jacobian of little f, and so d as written here, I'm just leaving all the superscripts k off. When b is the Hessian, we just get minus Jacobian f, inverse I need to choose, of course. Here we need to choose the inverse. So the metric we're choosing is the inverse of the Hessian. Or did I just write it differently here? Yes. Not a typo. So important, we need to choose, if we choose the metric bk or the matrix bk to be the inverse of the Hessian of capital F, then essentially here we have recovered Newton's method. Okay, so the step direction we're taking is minus grad f inverse f, or minus Jacobian of f inverse f. And if we choose alpha to be 1, then we have recovered Newton's method. And in the next section, we'll derive this link in a slightly different way in order to, what it says already in the title, globalize Newton's method. So we want to basically converge from any starting guess. So let me just pin down what this next section is about. Okay, this is not 4.2. This is 4.3. This is 4.3.1. So again, I say convergence of Newton is only local. And faster, the closer to the solution we start. So we need good initial guesses. So finding good initial guesses is an important task. So let's start by what we could pick. Remember, we are still in this whole lecture talking about, or at least in the previous chapters, talking about solving initial value problems. And we are solving these initial value problems in this time-stepping procedure. So a reasonable, and actually one very good choice, is a reasonable initial guess for our method for finding y1 seems to be, in a one-step method, seems to be y0, of course. But on closer inspection, and we did this already above when we discussed the fixed point iteration, that this is true only if the time step is small. Relative to the Lipschitz constant capital L. Now, the convergence requirements of Newton's method would then just impose new time step restrictions. We don't want to do this. We want to take the time step as large as the stability of our method allows it, or as large as the accuracy we want to achieve with our method allows. So which we want to avoid. And therefore, we now present methods, in particular one practical method, very practical methods which guarantee global convergence. So global meaning not convergence to the global minimum, but globally from any starting vector it converges to some stationary point of the minimization problem. And the local convergence should be quadratic. So P equals 2. And as a rule, and this is really now an important rule for any of your future mathematical endeavors and for anywhere where you're confronted with nonlinear equations, you should never use Newton's method without such a globalization strategy. I'm only giving one, namely the line search strategy. There's also another one called trust region methods, but I'm not going to dwell on that. Again, I'll refer to Notchedal and Wright for that. So under the assumptions of theorem 6, we can think of Newton's method of theorem 6, that can't be right, of theorem 4.1.4. Newton's method applied to the root finding problem f of x equals 0 for vector valued f from Rd to Rd is in fact a descent method applied to the functional capital F of x is Euclidean norm of f of x squared. So this is now the link that I said that for we can typically always find a capital F for which we do the minimization problem from the previous, so that the gradient of f is in fact that it actually solves the minimization problem. Okay, so this is not so grad capital F is not going to be little f in this setting, which we see immediately, but it still minimizes the still solves the root finding problem. So this is a slight detour from what we wrote down before. So the multivariate product rule applied to capital F gives that the gradient, that is a vector, of f of x is nothing else than 2 times the little f of x transposed in a derivative grad f of x. Or maybe we should do it the other way around first, then it's easier to see. I put the intermediate step in. So we have df of x, sorry, d little f no. It is exactly what I had written. Again, breaking my own rule. Don't change your lecture notes while you're writing in a lecture. Okay, so 2 times, so the outer derivative is essentially just, because this is nothing else than f1 of x squared plus f2 of x squared plus f3 of x squared, etc. So each component is essentially just f1, f2, f3, f4. So this would be f of x transposed times the derivative of the vector valued functions, which is the Jacobian nabla f of x. Now the search direction of the Newton applied to f is dk was essentially minus Jacobian of f evaluated at xk inverse f of xk. Now assume that f of xk is non-zero, then omitting the arguments xk, we have grad f times dk is equal to well, let's write it in transposes immediately. Something is not quite right here. Okay, I need to check this. I think that I made a mistake here. I think this should be the other way around. I'm gonna have to check this. I'll clarify it in the question and answer session and on the web. So I think this should be the other way around. That's why I got stuck here before. So I think this should be 2 grad f of x transposed f of x, and therefore if I substitute here, I get 2 times minus from here minus 2 times f of x transposed grad f. Well, we're dropping all the arguments we said. So f transpose grad f, and then grad f inverse f. And that basically is cancels here. So we see that this thing here cancels, and we end up with minus 2 times norm f squared, which is clearly, oops, we can write this in black again. So we end up with minus 2 times norm f squared, which is clearly less than 0. So it's and thus I need to check this, and thus dk is a descent direction that satisfies 4.6. And here we used that the fact that xk is sufficiently, that for xk sufficiently close to x star, we have that this Jacobian inverse is in fact existent, is bounded, and this can be found by the perturbation theorem. So if you look at the proof for the Newton convergence in numeric 0, then you see why for xk sufficiently close to x star the inverse exists and the norm of the inverse is bounded, and then finally choosing alpha k equals 1, we have established equivalence. Okay, so I'm gonna stop here because I promised I'll stop a bit early in this lecture, but we'll now come up with a practical method for Newton's method to be globally convergent by simply combining the Newton direction with the line search approach that I had before, and then we'll even make it more practically interesting by choosing an approximate line search, namely backtracking line search, and show that this is sufficient to get a globally converging strategy. But I'll continue with that next week. Okay.